China's scientists have just unveiled something extraordinary. The world's first intelligent chip that can operate across the entire wireless spectrum, from 0.5 to 115 gigahertz. Published in Nature, this breakthrough could unlock 6G speeds over 120 gigabits per second, and it does it with stability no system has achieved before. In this video, we'll break down how this chip works, why experts call it a game changer, and what it means for the future of global communication technology. The breakthrough rests on thin-film lithium niobate, a photonic material celebrated for its ability to manipulate light with precision. What makes this chip special is that it merges optics and electronics into one integrated system, called optoelectronic fusion technology. Instead of working within a narrow band, like traditional devices, it spans nearly 8 octaves of frequencies, from 0.5 gigahertz to 115 gigahertz. That range is unprecedented in wireless hardware. Ordinary communication devices are limited because each frequency band requires different materials and designs. Think of it as instruments in an orchestra, each able to play only one part. This chip, however, is like the conductor and the orchestra combined, playing across the full spectrum on command. The research team, led by Professor Wang Xingjuan and researcher Xu Haowen from Peking University and Professor Wang Cheng from City University of Hong Kong, built what they call an ultra-broadband optoelectronic fusion wireless transceiver engine. The key is a new optoelectronic oscillator, OEO. Traditional designs use frequency multipliers, which generate excess noise at higher ranges. Instead, this OEO employs optical microring resonators that act as filters, selecting and locking frequencies with remarkable stability. This allows the chip to generate low-noise carrier and local oscillator signals anywhere within its wide frequency span. More importantly, it can switch in real time, adapting instantly to the most suitable band. By removing the trade-offs between bandwidth, noise performance, and reconfigurability, the chip solves a challenge engineers have struggled with for decades. It isn't just a faster system. It's a platform that redefines how wireless communication can be designed. With this foundation, the line between photonics and electronics in communication technology has effectively been erased. Any bold new concept needs proof, and this chip delivers. In tests, it achieved wireless transmission speeds exceeding 120 gigabits per second, already hitting the peak thresholds envisioned for 6G communication systems. Yet its true strength isn't just raw speed. It's the ability to maintain consistent performance across every frequency band. Traditional communication hardware forces engineers into compromises. Low-frequency bands travel far and penetrate buildings, but can't handle high data rates. High-frequency bands, such as millimeter waves, deliver immense speeds but suffer from short range and signal instability. Usually, separate devices are needed to cover both, each optimized for a narrow task. This chip does away with that problem, bridging low and high bands in one platform. The secret lies in its optoelectronic oscillator design. Instead of stacking frequency multipliers, which pile up phase noise and degrade signal quality at high ranges, the system uses microring resonators. These optical structures directly lock frequencies with accuracy, producing low-noise carriers without the instability of older methods. The result is clean, reliable performance across its ultra-wide spectrum. In practical terms, this means a device built with this chip could adjust instantly. For long-distance transmission, it could operate in low bands. For fast, short-range transfers, it could switch to high bands. And it would do so without swapping components or suffering performance drops. Demonstrations confirmed this adaptability. Even in the high-frequency regions where traditional systems typically degrade, the chip maintains steady end-to-end communication. That stability clears one of the last big hurdles toward practical terahertz communication and future networks. With its proven results, this chip is more than an experiment. It's a demonstration that unified, full-band communication is no longer theory, it's reality. The implications of this chip go far beyond lab results. It is designed for AI-native networks, where systems can automatically adapt to changing environments. Built-in algorithms allow it to dynamically adjust parameters like frequency and power, ensuring optimal performance even in crowded or shifting electromagnetic conditions. Take base stations as an example. Today, They need separate modules to handle different frequency bands, which adds bulk and cost. A base station powered by this chip could integrate everything into a single unit, making networks smaller, cheaper, and more efficient. The same applies to vehicular communication systems. Cars equipped with the chip could seamlessly switch between low-band long-distance links and high-band short-range data sharing. That's a crucial capability for connected transport and autonomous driving. The technology also impacts the broader ecosystem of antennas, receivers, and optoelectronic modules. With a chip that can handle the full spectrum, manufacturers can redesign these components around a common standard, simplifying production and cutting costs while boosting performance. Looking ahead, this breakthrough supports the rollout of 6G networks and beyond. With verified speeds of 120 gigabits per second and stability across all bands, it opens doors to terahertz communication, immersive extended reality applications, and advanced satellite systems. Even higher frequency resources, once dismissed as impractical, could now become accessible. Publishing the results in Nature signals both scientific validation and international recognition. It highlights not just a technical leap, but a roadmap for building networks that are intelligent, adaptive, and unified. For everyday users, this means faster and more reliable connections. For industries, it marks the start of a transformation from materials to systems to entire communication infrastructures. In short, this chip is a foundation for the next era of connectivity. This new chip isn't just about faster downloads. It's about reshaping the future of how we connect. By spanning the full wireless spectrum, reaching speeds over 120 gigabits per second, and adapting intelligently to its environment, it sets the stage for truly unified 6G networks. From smarter base stations to connected vehicles and advanced satellites, its impact could touch every corner of communication technology. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. And don't forget to leave a comment below. Thank you for watching, and see you next time.